Okay, this is Refraction Worksheet 2. I'm choosing to go through this now for you to record down because this is a slightly harder portion of the chapter of light. Okay, let's look at the first question. Define refractive index of a medium in terms of the speed of light. So, refractive index, which is this n over here, is actually telling you how slow the light slows down by, okay, when it travels from air into whatever medium. So, for example, if I got the n of glass, okay, we know it's approximately 1.5. So we know that when light travels from air into glass, okay, the light will slow down by about 1.5 times. So if going by that idea, okay, refractive index n, okay, is the ratio of the speed of light in vacuum to the speed of light in the medium. This is actually the formula for one of the formula for refractive index, which is n equals to speed of light in vacuum, or sometimes can be air, divided by the speed of light in the medium. Okay, so this is one of the formula that you will see, which in summary is actually C over V in your textbook. Okay, I prefer to write it in this SOL in vacuum over SOL in medium because it's easier to remember what should go on top and what should go to the bottom. Okay, now for the next part, we're gonna look at a little phenomenon, okay, but let's go through step by step. So first one, okay, 2A, undeviated light ray. Now imagine this is a ray box, or it is a ray box. When we are shining, it actually shoots out a ray of light. So when the ray of light goes through the circumference to the center of the circle, you realize that the light ray is not deviated. Okay, at this point here, there's no bending of light. Why is it so? It's because this is one of the property of a circle. Okay, so if the light ray or anything travels from the circumference to the middle of the circle, okay, sorry, I think that I got some thing. When it travels from the circumference to the middle of the circle, okay, so from here going to here, the light ray is actually traveling along the normal. Light ray will actually travel along the normal. So when the light ray travels along normal, comma, it will not bend, but it will slow down. Okay, so refraction, one of the key ideas here is that the light will actually slow down. We do know that it will tend to bend, but in this case here, because the light is traveling along the normal, the angle of incidence is actually 0 degrees. Okay, the angle of incidence is actually 0 degrees. So if the angle of incidence is 0, the angle of refraction would naturally be 0 because there's no other direction to bend. Now, the next focus would be here. Okay, when light rays travel from a denser medium to a less dense medium, we will normally think that it should bend away from the normal. However, once again, it's the same phenomenon here. The light rays traveling along the normal. So if it's traveling along the normal, the light ray wouldn't bend. Okay, it will just it will still undergo refraction in terms of changing its speed, but in this case here, it will not bend. So if I go to the part here, a light ray that passes along the radius of a semicircle glass box will not bend as its path is perpendicular to the tangent at the point of entry. That means it's traveling along the normal. Okay, so just take note of this. The next one, okay, instead of shooting it from this point over here, instead of shooting like that, we now shift the ray box over to this side so the light ray projects this way. Okay, so we have shifted it slightly. Now, so what happens now if the ray box is shifted slightly? Once again, at this particular point over here, at this particular point, no bending of light. okay, but the light still slows down. Okay, why is it so? Do take note, because it's traveling along the normal. Okay, now, but when it reaches at this point, so now let's consider this particular point over here. Okay, oops, sorry, point over there. So when the light ray strikes at this point, we know that it will exit the semicircle glass block. So this is the refracted ray. Okay, sorry, so over here, this is a refracted ray. Okay, now, in all situations, normally there will be some light reflected. So about 10% is reflected. But to keep things simple for us, okay, I just want you all to just ignore this line. Let's just focus on the incident ray over here and the refracted ray over here. Okay, so we know that the semicircular glass block would be denser. Outside here would most probably be air or vacuum. It will be less dense. So as it travels from the denser medium to optically denser medium to optically less dense medium, you will know that it will bend away from the normal. Okay, we also know that it will become faster. So first thing, bend away from normal. Second thing, it will become faster. So based on the understanding, it says based on the text here, now let's look at it. A light ray that passes directly at an angle of incidence I at O. Okay, so with the angle incidence I here, the refracted emerging light ray from the glass block is bent away from the normal as it is traveling from an optically denser medium to an optically less dense medium. Okay, so this is in terms of a normal refraction that I've gone through in worksheet 1. Now this is the part where it gets a little bit interesting. Okay, you realize that the light ray is bending away from normal here. What happens if I increase the angle I? So if I increase it more and more and more, it will come to the next scenario. Okay, now let's once again ignore this light ray over here, this weak refracted light ray. Now if I increase the angle of incidence more and more and more and more and more, okay, there will come to a situation where the angle of refraction becomes 90 degrees. Okay, so I say again, when I increase the angle of incidence more and more and more and more, you will see that, oh, there will come to a point in time where the angle of refraction becomes 90 degrees. What we will say is that for this angle of incidence that produces this angle of refraction equals to 90 degrees, we give this angle of incidence a special name. We call it the critical angle. So the critical angle or the critical angle is a very specific angle of incidence for each medium. Okay, because it produces this phenomenon where the angle of refraction is 90 degrees. So let's look at the wording over here. As the angle of incidence I increases, the angle of refraction R also increases until a point where R equals to 90 degrees. Okay, the angle of incidence in the glass block, comma, at which the angle of refraction is 90 degrees, comma, is known as the critical angle. Okay, critical angle. Now, this phenomenon here is still refraction. It's just that it's a little bit special because the angle of refraction is 90 degrees. Now, question is, what happens if I increase the angle of incidence even more? You realize, oh, if I increase it even more, what's going to happen to my this light ray over here? It will start to bend into, it will start to bend back into the medium. Okay, so do take note, when it bends back into the medium, it doesn't gradually bend. Instead, it doesn't go, the light doesn't go out, it gets reflected. Okay, when I increase the angle incidence greater than the critical angle, when it goes beyond this critical angle, okay, this specific number, the light ray doesn't go out anymore. The light ray actually gets reflected back into the medium. We term this as total internal reflection. So let's do a bit of a understanding of diagram here. So the ray box has been shifted in such a way that this angle of incidence is now greater than the critical angle. So maybe previously it was like 40 degrees. Now maybe I increase it to 41 or 42 or maybe 43 or maybe 50 or 60. Doesn't really matter. As long as it's bigger than the critical angle, okay, that we have measured previously. So if it is greater than the critical angle, this idea called the total internal reflection occurs. Okay, so light ray get reflected back into the medium. So this portion behaves a little bit like a mirror. Okay, but it's not a mirror. Do take note of that. It behaves like a mirror. So the light ray gets reflected back. Okay, so the light ray travels this way and it gets reflected back. So now, once you get reflected back, okay, you realize that the angle of incidence, angle of reflection is the same because this obeys the law of reflection. So let's do a little bit of looking at the text over here. As the angle of incidence I increases to a value greater than the critical angle, the angle of refraction cannot increase further. So no light gets refracted through the glass air boundary. 100% of the light gets reflected back to the glass block. This is known as the total internal reflection. Okay, do take note of that. So this portion at the top there is just for you to understand a little bit on what happens when refraction goes to the extreme. Okay, where if I keep increasing the angle of incidence greater and greater and greater, you realize that it will come to a point where the light ray, the angle of refraction becomes 90, and if it goes beyond that, it becomes what we call this phenomenon, total internal reflection.